Okay, so now we will review module 1, analyzing the efficiency of algorithms. So what we want to do is derive an expression for the average number of key comparisons in the sequential search algorithm. So what is the sequential search algorithm? Given an array, we want to find whether a particular key, a search key, is in the array or not. Okay, so which means the array could would be given to you, or given the array. So for example, something like this. Okay, so you want to then search for a key. So this is a sequential search. So you will given a key k, you will search whether k is equal to this number. If not, we'll search whether it is equal to this one. If not, and so on until you find the key there, or we reach the end of the array and the key is not there. Okay. So you're given, say, the probability p of finding a particular key or any key in the array. Okay, so p is the probability of finding an element in the list. Okay, then 1 minus p is the probability that the element you're searching for is not in the list. Okay, so now the element that you're searching for can be anywhere in the list. It can be equally distributed in index 0, index 1, and so on. Alright, so if p is the probability of finding an element in the array, then p over n is the probability of finding the element in a particular index of the array. Okay, because the array has n elements, right? So what is the probability that the search key you're finding is in a particular index is p over n. If that is the case, then remember here the basic operation is comparison. You're comparing whether the key is equal to any of these elements in the array. So essentially what we are having is you are counting the number of comparisons, right? So if the search key is the first element in the array, then you will be doing 1 times p over n. That's the average number of comparisons, right? If the search key is the second element in the array, then you'll be doing 2 comparisons. So 2 times p over n. So the element could be either the first element in the array, or the second element, or the third element, and so on, or it could be the last element in the array. So when you're having an OR, you can't do the average number of comparisons, you're doing a weighted average. So you're basically adding up all the possible probabilities. So 1 times p over n if it's the first element, and 2 times p over n if the second element. So you're counting the number of comparisons depending on the probability the element could exist in any of those particular index values, right? So this is the case if the this portion is the case if the element is in the array. Then if the element is not in the array, that's the probability of 1 minus p, we would do n comparisons, right? Because we will go through the entire array. So that is the expression for the average number of comparisons. So then we can take this p over n outside, and we can say it is 1 plus 2 plus so on up to n plus n times 1 minus p. So that is p over n, and now this is n times n plus 1 over 2 plus n times 1 minus p. So n and n can cancel, so it is p times n plus 1 over 2 plus n times 1 minus p. So this is the expression for the average number of comparisons. Now if you substitute the individual cases, if p equals 1 means the element that you are searching for, any element that you are searching for, is guaranteed to be in the array. So if I substitute p equals 1, this comes out to the average number of comparisons is n plus 1 over 2 plus, if p is 1, this term goes to 0. So it is simply n plus 1 over 2. If p is 0, which means whatever you are searching for is not going to be the array for definitely, then p is 0, so this term goes to 0, so this is n times 1 minus 0, which is n. So we'll be doing at the worst case n comparisons. Okay, so now you can also plug in the numbers that you're given here. You have a 10 element array, so n is 10, probability of finding any element is 0.3, so just substitute 10 and 0.3 here. You'll get 0.3 times 10 plus 1 over 2, so that is 0.3 times 11 over 2, plus this is 10 times 1 minus 0.3, so 10 times 0.7, so that comes to 8.65. Okay. So the best case in sequential search happens if the search key is the first element in the array. Okay, and the worst case happens if you have to search the entire array if the element is not there or is the last element in the array. And the average number of, so in worst case you will do n comparisons, right? And the average case you will do n plus 1 over 2 comparisons if you know that the element you are searching for is in the array. Okay. Then this proof of the property for this big O notation. So if a function t1 of n belongs to the class big O of g1 of n and t2 of n is big O of g2 of n, then t1 plus t2 is going to be big O of the maximum of g1 and g2. Okay, so to prove this, what we will do is we'll use the definitions of big O. So if t1 of n is, so if t1 of n is c1 of g1 of so if t1 of n is big O of g1 of n, then t1 of n can be represented as less than or equal to some constant c1 times g1 of n for all n greater than or equal to n1. Right, so this is from definition of big O notation. Similarly, if t2 of n is big O of g2 of n, then t2 of n is some constant times c2 times g2 of n for all n greater than or equal to n2. Right, so this just by definition. Now, if t1 plus t2, this is what you want to find, right? So let's introduce two constants now, c3, which is the maximum of c1 and c2, and n0 is kind of the maximum of these two numbers, n1 and n2. Right, so now t1 plus t2 is going to be less than or equal to, because we have t1 is less than or equal to c1 g1 and t2 is less than or equal to c2 g2. So I can say t1 plus t2 is less than or equal to c1 g1 plus c2 g2. Right, so now is where we are going to introduce these two constants, or kind of get rid of c1 and c2 and introduce c3. Okay, so this is something like this. If you have say 2g1, right, plus 3g2, right, I'm going to say this is going to be less than or equal to 3g1 plus 3g2. Why is that? Because if you kind of put the maximum of these two integers, it's going to be always less than or equal to, right? So that's what we have here. We have defined c3 to be the maximum of c1 and c2. So we can say c1 g1 plus c2 g2 is going to be less than or equal to c3 g1 plus c3 g2. So now I can take this g3 as a common constant outside, and I can say this is c3 times g1 of n plus g2 of n. Okay, so now I'm going to do the same thing here. So if you have two functions, g1 of n, right, g2 of n, so we can say this is going to be less than or equal to twice the maximum of g1 of n, comma g2 of n. Why is that? Like again, if you have 3 and 5 just in numbers, and this is going to be less than or equal to twice the maximum of 3 and 5, right? So g1 of n plus g2 of n is less than or equal to twice the maximum of the two function values, right? So now that's what I have done here. I'm going to combine these two C3 into a new constant, and so that's looking like the definition now. T1 plus T2 is less than or equal to a constant times the maximum of G1 and G2. So we can say T1 plus T2 is big O of the maximum of G1 and G2. So we are now going to introduce a constant n um, 0, that is the maximum of n on n2, because this holds good for n greater than or equal to n1. T1 is less than C1. Then T2 is less than or equal to C2 for some constant n greater than or equal to n2, right? For any n greater than or equal to n2. So now we have T1 plus T2 is less than or equal to the big O maximum of G1 and G2 for n greater than or equal to some constant n0, which is a maximum of n1 and n2. Okay. Alright, so let's see. We want to evaluate the simplest theta of g of n for each of this. So you need to use the limits approach, that is a L'Hopital's rule. So you want to find for n square plus 1 raised to 10. Okay. So you see the highest exponent is kind of 2 here and then is raised to 10. So you want to find a theta here. So you want the same kind of exponent as the theta of g of n. So that's why we'll choose this is n to the 20. That's our hypothesis, will be our g of n. And we need to verify the hypothesis using the limits approach now. So we'll take limit n tends to infinity n square plus 1 raised to 10 divided by n raised to 20. So I can write my n raised to 20 as n square raised to 10. That's what I did here, and I can say this is n square plus 1 divided by n square, right? The whole thing raised to 10. So this is 1 plus n square, the whole thing raised to 10. Limit n tends to infinity, this term becomes 0 then. So 1 raised to 10 is 1. It's a constant. So which means both the numerator and the denominator grow at the same rate as n tends to infinity. So you can say n square plus 1, the whole thing raised to 10 is theta of n raised to 20. Okay. So now this function, square root of 10n square plus 7n plus 3, again the highest exponent here is n square, and then you are taking a square root. So square root of n square is kind of like n. So our hypothesis is this will be equal to theta of n. So we'll do now limit n tends to infinity, square root of 10n square plus 7n plus 3 divided by n. But now we can write our n as square root of n square. So that then we can take n square inside, the whole thing will be a square root. So it is 10n square plus 7n plus 3 divided by n square, the whole thing under square root. So n square cancels, then 10 plus 7 over n plus 3 over n square. So now if you apply the limits, n tends to infinity, this is equal to square root of 10. So it's again a constant, so we can say now square root of 10n square plus 7n plus 3 is theta of n. Okay. So now this is 2n log n plus 2 whole square plus n plus 2 whole square log n over 2. Okay. Now you see here we went this over in class. If you have log n square, right, log of n square. Okay, so I can say this is log of n times n, so that is log n plus log n, so that is 2 log n. Okay. So likewise, if you have log n cube, then it's going to be 3 log n. Okay. Because you can say log of n times n, so that is log of n plus log n plus log n, so it is 3 log n. So I can say this is equal to 4, okay, 2n log n plus, so that is going to be like 4n log n plus 2 plus n plus 2 whole square log n over 2. So this is nothing but theta of n log n plus theta of n square log n. So that's going to be theta of n square log n. Okay. Then 2 to the n plus 1 plus 3 to the n minus 1. So I can say this is 1 over 2 times, sorry, not 2 to the n plus 1 is 2 to the n times 2, right? Then this is 3 to the n over 3 because 3 to the n minus 1. So I can say this is theta of 2 to the n plus theta of 3 to the n, and between these two functions 2 to the n and 3 to the n, 3 to the n grows faster, so you can say this is equal to theta of 3 to the n. Okay, and the formal definitions we saw that because you can say t of n is equal to big O of g of n if t of n is less than or equal to some constant times g of n for all n greater than equal to n0. So it means after this point t of n grows only slower compared to g of n. So g of n grows faster. Okay. So always t of n is going to be less than or equal to some constant times g of n. Now for this big omega is the opposite of that. T of n is always going to be greater than or equal to c times g of n for some constant n greater than or equal to n0. So t of n is going to be bounded actually below by c times g of n. Now we can say t of n is theta of g of n if t of n grows at the same rate as g of n. So that's why after a constant n0, t of n is some constant c1 times g of n. So the extent of the growth rate differs just by this constant, and the t of n is equal to some, and then something like this. It's always greater than or equal to c2 times g of n, but it is less than or equal to some constant c1 times g of n. So the growth rate, as I said, differs only by constant. Now if you want to prove the same inequality that we proved before for big O, for this big omega notation, then we have to do the other way here using the minimum here, because if t1 is big omega of g1 and t2 is big omega of g2, what we want to prove is t1 plus t2 is big omega of the minimum of g1 and g2. Okay, so the way we do that is this again by using definitions. If t1 of n is big omega of g1 of n, then t1 of n is going to be greater than or equal to some constant c1 times g1 of n for n greater than equal to n1. Similarly, if t2 is equal to big omega of g2, then t2 of n is greater than or equal to some constant c2 times g2 of n. So you can now add them. So t1 plus t2 is c1 g1 plus c2 g2. So now I can introduce, so now this holds good for some n greater than or equal to the minimum of n1 and n2, because we're taking the minimum here. Okay. So let's introduce c3 to be a constant, which is again the minimum of c1 and c2. So this is going to be the right side of this. c1 g1 plus c2 g2 is going to be greater than or equal to c3 g1 plus c3 g2. So like if you have 3 plus 5, this is going to be greater than or equal to twice the minimum of 3 and 5, right? So that's what we do, isn't it? So similarly, if you have okay, so I can take my c3 out, the c3 times g1 plus g2, then g1 plus g2 is going to be greater than or equal to twice the minimum of g1 plus g1 or g2, right? Minimum. So I can say this, I can say 4 plus 3 is going to be greater than or equal to twice the minimum of 4 and 3. So t1 plus t2 is greater than or equal to 2 times c3, minimum of g1 and g2. So that's going to be big O of g1, minimum of g1 and g2. So we'll stop with this.